Hello, today we're going to do the multivariable version of the chain rule. So, if we remember the chain rule from last semester, if we have a function f of x and x is also a function of t, i.e. we have x as a function of t, the chain rule says if we want to take the derivative of y equals f of x and we want the derivative of y in terms of t, what we had to do was take the derivative of y in terms of x, okay, and then multiply it by the derivative of x in terms of y. So the multivariable version is similar. But this time we have more variables. Let's say we have a function z equals f of xy, and x is a function of t, and y is a function of t. Okay? If we want to do dz dt, we would have to do dz dx times dx dt plus dz dy times dy dt. Now, so it's really similar. The way we thought about this last semester was, although these are not fractions, they kind of behave like fractions. If you want dy dt, you could kind of cancel these out. Again, these are not fractions, they're infinitesimals, but that's what the chain rule says. So the first derivatives behave like fractions in some sense. So we have almost the same thing here, but z is a function of x and y, and x and y are both a function of a third variable t. Okay, so we're going to call these guys the intermediate variables. X and y are the intermediate variables. Okay, so z looks like a function of x and y, but it really isn't. T is the free variable. It's actually a function of t. Okay, I'll show some examples of how this might be useful later on. Okay, so let's move on and think about how this applies. So again, if you want the dz dt, the dx's can kind of cancel. You get the dz dt here, and you get a dz dt here when the dy's cancel out, kind of. So you might think, hey, hold on a second, I don't get one dz dt, I get two dz dt's. You don't really, but I'm not going to go into the reasons of that, because again, chain rule is one of those theorems that are actually a little bit complicated. It's above the level of a ordinary calculus class. I'm not going to go into it. The way to remember this is very simple. We just draw a diagram. So we have the variable z, and we know that it is in terms of x and y. Okay, and we know that x and y are variables in terms of t. Okay, so I think about how do I go to t? Well, I have to go from z to x and x to t, so I'm going to do dz dx times dz dx dt, and I can go to t this way through y, so I'm going to do dz dy times dy dt. Okay, so if we draw these diagrams, they're really helpful. Now let's do another example. You could have z, or a function of, say, three variables, and the three variables are intermediate variables, and let's say we could have two independent variables. So let's see an example. If we have let's say w as a function of three variables, x, y, z. They look like independent variables, but they really are not. And x is a variable of, let's say, t and s. Y is a variable of, let's say, function of t and s. And z is a function of t and s. Okay? How would we do the partials this time? So let's say I'm interested in, there's two partials that I can do. Well, it's a function of two variables at the end, isn't it? Okay? So I can get dw dt or dw ds. Okay, so again, I'm going to draw my diagram here to make it easier on me. I have x, the intermediate variable x, I have y, and I have z here. Now, this guy, all of these guys are actually independent variable of two guys, t and s. So y goes to t, y goes to s, z goes to t, z goes to s. Okay, so if I wanted to go to dw dt, I could go through x. So let's start writing that. Actually, we have dw dt. Well, I can go through x. That's going to be dw dx, okay, and dx dt times dx dt. Again, every single time the terms should cancel, and you should have what you want at the end. Plus, okay, I can go through y. I got dw dy times dy dt, okay, dw dy, dy dt, and I have dw dz times dz dt. Okay. Also, I could have done dw ds, dw ds. Now I can go to s through x, y, z. So it's going to have three terms again. We're going to do dw dx. Okay, I go through here, and then I'm going to go to x. So we're going to get dx ds. Again, you see that at the end of the day, when the dx is cancelled, if you think about it that way, they really don't, but if you think about it that way, we have dw ds plus, well, I can go through y, dy ds, plus I can go through z, we have dw dz times dz ds. Sorry, out of bounds there. Okay, so you see the general picture. You can have a function of as many variables as you want, and each of those variables might be defined in terms of some other variables. It really doesn't matter, and we can always kind of figure out which way we're going to go to which variable, and write down these equations. Now, of course, when we're looking at it from an engineering perspective, it really doesn't help us. You know, these formulas are nice, but we'd like to see them in action in a calculus class. So let's do an example. Let's do an example here with a function of two variables. So in our example, let's start very easy. Let's say we have z is equal to x squared plus x sine y, okay, and we have x is actually equal to square root of t, and y is equal to t cubed. Okay, so what we're going to ask is, well, we want to find dz dt. So the question is, what is dz dt? Okay, so we're going to apply the chain rule. Remember, we have z here, we have x here, we have y here, and we have t at the bottom. So dz dt as a formula, let's just write down the formula once more. We did it before, but let's do it again. We're going to get dz dx times dx dt plus dz dy times dy dt. Okay? So now let's just plug in everything we got. If we think about it, we have z defined here, okay? So when we're talking about here, I'm sorry, I'm writing them like normal derivatives. It's just my, my handwriting is horrible. But these are actually partial derivatives, so I should be doing funky d here, but I'm not going to do it. Well, I mean, if you do a lot of these, you kind of don't do that d sometimes. So these are partial derivatives. So I have to ask myself, what is the derivative of z with respect to x? Now, when I say that, I'm thinking of x as an independent variable and y as just like a constant. Okay, so sine y is just a constant for me. So dz dx, if I write dz dx, that would be just equal to 2x from here, okay? And this is a constant, so it's just x times constant. It's just like 5x, but it's now sine yx. So derivative of 5x would be 5. Derivative of sine yx is just going to be sine y. Okay? So we got this term, okay? And then we're going to need dx dt. Now, I'm actually going to move over to the next page, I think. Let's keep it here. Let's move over. So again, let me just write down the problem here so that we'll have it. Sorry, it didn't fit. We had z is equal to x squared plus x sine y, and x was equal to square t, and y was equal to t cubed. Okay, so we had our formula. So we calculated, remember, we just calculated dz dx. Okay, dz dx was 2x plus sine y. Now I need dx dt. What is dx dt going to be? This is t to the 1/2, so it's going to be comes in front 1/2, t to the minus 1/2, so it's going to be 1/2 square root t. Okay, and let's calculate dz dy. Okay, this time we're going to treat everything that has x as a constant. So whenever you see an x, it's just a number. Okay, think about it like 5 or something like that. dz dy, well, this is just a number for us now. So we're just going to, derivative of it with respect to y is just going to be 0. Okay, 0 plus. Now derivative of sine y, x is a constant, that would be just cosine y. So we have x times cosine y when we're talking about the partial. So it's actually just x times cosine y here. We got it. Now let's calculate dy dt. dy dt is going to be just 3t squared. Simple polynomial, no problem. So if we put everything together, then we get dz dt is equal to dz dx, 2x plus sine y times, the whole thing times 1/2 square root t, plus dz dy, we have x cosine y times 3t squared. Okay, now this is correct, but it's not nice. Why isn't it nice? It's not nice because remember, the original question was find dz dt. We wanted to find this guy. Now, when I say find dz dt, usually, I mean, if we're polite, I want everything in terms of t, okay? But I have x and y on both of these terms, so we should take an extra step and be nice and write everything in terms of t. Can I write everything in terms of t? Yeah, sure, I can. We are going to just plug in definition of x and, sorry, we are just going to plug in definition of x and y into this formula. Wherever we see an x, we're going to plug in square root t. Wherever we see y, we're going to plug in t cubed. So if I do that, what are we going to get? We're going to get 2 square root of x, okay? Sorry, 2 square t, my bad, I'm sorry. 2 square t plus sine y, so sine t cubed, all right, all over 2 square t, okay, plus, we had, let me carry the 3t squared over here, again, 3t squared times, we have t to the 1/2, that's square t, okay, cosine t cubed, okay, so, yeah, I mean, you can combine these, this is going to be t to the 2.5, right, or 5/2, whichever way you want to think about it, and we get this answer. Okay, so if we had a point given to us in terms of t, right, we could actually calculate the exact value to it. So if we had t equals, let's say we're interested in the derivative of z with respect to t at t equals 4, you just plug in 4 into everything and you get that. All right, so we will continue now with more examples and more applications of this. Let's do something that has that is different. We had a problem where we had two intermediate variables. Let's say now we have three intermediate variables and two independent variables. So here's our example. Here's our example. Let's say w is equal to xy squared z cubed. Okay, and let's say x is equal to s squared plus t squared. Okay, it's a function of two variables. Y is equal to, let's say, just t times s. Okay, and z is equal to square root of t times s. Okay, so we have a funky function like this. All right. So now this is going to have, sorry, this is a plus, my bad. We're going to have actually two derivatives that are possible here. The first derivative is we can talk about dw dt, and we can talk about dw ds. Now, if we draw our picture, remember w was here, x was here, y was here, z was here. W was a function of x, y, and z. All right, and x itself was a function of s and t. Y was a function of s and t, and finally z was also a function of s and t. Okay, so if we write down our formulas, we get, if we write down our formulas, we get the following. If we're interested in dw ds, we would need to go through three variables. We need to go to dw dx first, this way, and then I can go to ds through x, so it's going to be dx ds. Okay, plus we're going to talk about, we can go through y, so we can go dw dy, and then dy ds, right? And then finally I can go through z, dw dz, and then that's going to be dz ds. Okay? All right. So if we were interested in dw, not ds, but dt this time, it's the same thing. We go through x, we do dw dx, we go through dx, that's going to be dx dt. Okay, that's the only thing that's different. Instead of dx ds, we have dx dt. Again, note that when you cancel the dx's, you get dw dt. Each term should be dw dt. So we get dw dy. Now I want dy ds. I want dy dt plus dw dz times dz dt. Okay, so very good. Let's say we could calculate both of these just to save some time. Let's say we're just interested in dw dt. So the question we're going to assume it's going to ask us, what is dw dt? Okay, what is this stuff? All right, so the formula that I'm going to be interested in this formula. So I have to calculate all these partials. Let's do that. Let's try to do it in one shot. dw dt. We're kind of used to it. Now dw dx. When I say dw dx, of course x is the only variable. The other guys are just like constants. So when I take the derivative, I get y squared z cubed. Okay, times. Now I need to find dx dt. This is again a constant when we're thinking about the partial derivative. Sorry, you're not seeing what I'm looking at. I'm sorry. So this is 0. This is just going to be 2t. Okay, plus we have we have next term is dw dy. So y is our variable. So x times z cubed is a constant. So we're going to get 2x y z cubed. Okay, this was y squared, came in front. The other guys we don't play with because they're just constants. Times dy dt. Well, dy dt, this time s is a constant. Derivative of t is just 1, so it's going to be s. So times s. Oh, sorry, I'm talking about t. Sorry, I want to do not ds. I want dt. Okay, so it's just going to be. Sorry, I did the correct stuff. My bad. So s, right. Plus, we want to do dw dz. Well, this time it's going to be 3x y squared z squared. 3x y squared z squared times, okay, so here is again a chain rule inside a chain rule problem. We have this 1 over 2 square root of t times s times the derivative of the inside. Well, the derivative of the inside is just s. Okay, so now again, to be nice, we should plug in everything we see in terms of t and s. So plug in. Let me just write it here. It's going to be too long to fit on this paper. Maybe you could do it at home when you have to plug in t, s, and t to get the final answer. All right. So we did these examples, okay, but there's still, if you notice, there's still no problems, no numbers or anything like that. I want to do one more problem without any numbers, unfortunately, and then I'll do a word problem, hopefully, where we're going to see this stuff applied. Let me move this, and let's go on to our next page, guys. So okay, so I have a weird problem here. Let's say again, let's take a very simple function example. We have, let's say z is equal to 2x squared. Sorry, let's erase this. Okay, so it's equal to 2x squared plus 2y squared. All right. And we have s and t again, but s and t are equal to x minus y, and t is equal to, let's say, x plus y. Now this function, this is going to be a little weird, because I'm going to ask, let's say again, let's just do, I don't know, this time let's try to find what is dz ds. Okay, so dz ds, something's wrong here. Okay, the problem here is if we're trying to find dz ds, how am I going to do that? Z is a function of x and y. Okay, so I start doing my diagram and I go x and y, and hold on a second, x is supposed to be a function of s and t, right? And y is supposed to be a function of s and t, but instead s is a function of x and y, and t is a function of x and y. Okay, so what's going on here? Actually, two things we can do. What we can do is we can try to get, using these two formulas, we're going to try to be smart about this and actually find x in terms of t and s and y in terms of t and s. Okay, so as functions, these are simple enough that we can actually do this, right? So look at it. If I add s and t together, right? If I add these two functions together, I would get s is equal to x minus y, and remember t was equal to x plus y. So if I add these guys up, right, what I should get is s plus t is equal to, the y's cancel and you get 2x. Well, now I can do x is equal to just s plus t over 2, right? So this is nice because I got x now in terms of s and t. And similarly, if I subtract, right, if I subtract them, s is equal to x minus y, okay? T is equal to x plus y, all right? And now we subtract the second equation. We would get s minus t is equal to, well, this time x is going to cancel. We get minus 2y. Okay, so from here, we would get that y is equal to s minus t over minus 2. Or let's just make it nice. I can just switch these around. T minus s over 2. Okay, so now this is nice. This is nice. So remember, we were being asked dc ds, and now through this small amount of work, I have x and y as functions of s and t. Okay, not too bad, is it? S, t, s, t. Okay, so you can't always do this, but sometimes you can. You can do it without much effort. It's sometimes like these linear algebra problems where you add them or subtract them or some multiple of them. Sometimes you have to do I use the identity cosine squared plus sine squared equals 1. You're not going to be asked ones that are very difficult, okay? You're not going to be asked ones that are going to be very difficult probably. So it's going to be, I mean, just don't panic and try to choose those two equations to get what you want. Now, I wanted these dz/ds. Now I can write dz/ds, right? dz/ds was equal to dz/dx. I can go through x times dx/ds. Great. Okay. Plus, or I can go through y, and I can get dz/dy times dy/ds. Okay, so let's put this all together now. Let's put this all together. Hopefully you can still see the original problem. We have dz/dx. What is dz/dx? Well, this is just 0, so that's just going to be 4x times, all right. What is dx/ds? Well, I'm going to use this formula, okay? Because now x is in terms of s and t, so I'm interested in the partial with respect to s. That's just going to be s over 2, right? Okay. This is just so this is s over 2 plus t over 2. T over 2 is 0, right? Derivative of it. So this is just 1/2. Okay, 1/2. Okay, plus let's look at dz/dy. Similarly, that guy is going to be just 4y. Okay, because 2x squared in terms of y, that's a constant. It's 0. And we have dy/ds. Well, not too hard either. dy/ds. Now I look at this equation, right? It's just going to be minus 1/2. Again, it's t over 2 minus s over 2. T over 2 is 0. Derivative of it is 0. Minus s over 2, you're going to get minus 1/2 from there. Okay, so when the dust settles, let's get, we get 4x. Sorry, let me plug in what x was. X was s plus t over 2, okay, times we have another 1 over 2, all right, plus, let's try to fit in here, we have, this time it's going to be minus 4, so we can just make this minus 4. Y is actually, well, let me do that in another step. T minus s over 2 times we have times 1 over 2. All right, so we can actually clean this up more, can't we? Well, what we can do is the following. These 4s are going to go, okay, so this guy and this guy and this guy and this guy is going to go away. And now because it's a minus, I can write this as s minus t. So we have s plus t plus, right, s minus t, and that's just equal to 2s. All right, so we did find it. It's just equal to 2s. Similarly, why don't you try to do dz dt, do dz dt on your own. What is that? Maybe you could take a few minutes and do it. after watching this vid. But the thing that I want to mention is whenever you get a simple answer like this, okay, something must be going on. That's what at least I think. Now, what I can realize is, of course, when the original problem was given like this, another thing we can do to check our work, we did this problem on purpose, so we can do it two ways, is, well, I can straight plug in these values, okay, hopefully into here, okay, somehow, and write z in terms of s, okay. Well, can I? Yes, I sure can, because once I solve these, right, once I have x in terms of s and t and y in terms of s and t, well, I can just plug in, just square them and just get z in terms of s. Let's do that, okay? So remember, so as a summary, remember we had z is equal to 2x squared plus 2y squared. So this is another way, second way, just to check our work. And because it's nice, it shows you that the chain rule actually works. You don't have to, of course, there's a proof of it, so it absolutely works. But you can see it with your own eyes that it actually works. So we had this, and remember we concluded that dx, sorry, my bad, not dx, x was equal to s plus t over 2, okay? And y was equal to t minus s over 2, okay? So we did that all that work up here, remember, I'm just carrying it over so that we can do it. So then, if we plug it in, z is going to be 2 times s plus t over 2, the whole thing squared, right? And y is going to be 2 times 2y squared is going to be t minus s over 2, the whole thing squared. So if we do this, what are we going to get? Well, I'll get 2 times, here we're going to get s squared plus, well, I'll have 2st plus t squared over 4, right? Okay. Plus 2 times, I'm going to get, again, t squared. This time it's going to be minus 2st, okay, plus s squared over 4. Now I see something going on. There's going to be 4st minus 4st, so these terms, these st terms are going to cancel each other out, okay? And at the end of the day, so once they cancel each other out, I think, and I can cancel this 2 and 4, this 2 and 4, I'll have 1/2. I think what I'm going to have is I'm going to have a 1/2 s squared from here, and another 1/2 s squared from here, so that's just going to be s squared, right? And then I'm going to have t squared over 2 from here, okay? And I'm going to have t squared over 2 from here, so I'm going to have t squared. All right, so what is this? This is z is equal to s squared plus t squared. So it kind of looks like the original function, doesn't it? Little funky. So now, is it difficult to calculate dz ds from here? No. Well, if you do it this way, it's just 2s. But look, that's the exact same answer we got using the chain rule. Now, of course, this problem is simple enough that you can just skip the chain rule and do this. But in general, you really can't, okay? Or it doesn't make sense to do it. Okay, so I promised the word problem. I'd like to do a word problem now. By the way, you can clearly see that dzt would be 2t. So if you go home and do the chain rule, you should get 2t after substitution. That's kind of a, hint. But let's do a word problem, to see how we could apply this in a real life situation. Well, everything's going to be kind of nice, so it's not going to be real life. But anyhow, let's say, as an example, we have a water tank shaped like a cone. Okay. So water tank. shaped like a cone. Okay, so I don't know why you'd have a water tank shaped like a cone, but anyhow, for our example it is. What can you do? I'm not going to give the dimensions of it or anything like that, okay? The issue here is we have some kind of tab here, okay? We have some kind of tab here, and the water is coming out. We open the tap, okay? There's a tab. There's a tab at the bottom, and we open it up. Once opened, of course, water is gonna decrease. Okay, so at any given moment, we have the volume in terms of course, the radius and height, but something's going on with the volume in terms of time, of course. Now, the problem here is when the height of the water is 8 meters, and the radius, of course, the radius of the cone at that height, okay, radius is, let's say, 4 meters. 4 meters. The height is decreasing 0.5 meters per second, okay, and radius is decreasing let's say at 0.4 meters per second, okay. So the question is going to ask, find the SD is for it. So for dV dt, okay, or in other words, i.e. rate of change of volume with respect to t at that given moment when the height is 8 meters and the radius is 4 meters. Okay, so alright, we can handle this, I think. So the question is asking dV dt, right? So that's what it's asking. Now, let's do our shape here. Well, what do we know? Volume is really described in terms of R and H. Why? Because we know the volume of a cone, right? And that's equal to pi R squared H over 3. So it is a function of R and H, okay? And here, R and H isn't described in terms of t because your given height and radius is going to be time dependent, okay, because as the water is flowing out. Okay, so if I do this, well, what should I do? I should do dV dr, right? That's the first variable, times dr dt plus, well, I can go through h, so I should do dV dh times dh dt. Okay, so let's plug in everything and see what we have. Now, what is dV dr? Volume is equal to pi r squared h, so we're treating only r as a variable, so it's going to be 2 pi r h, okay, 2 pi r h over 3, times, we're given that the radius is changing at that moment 0 point, so this is dr dt, isn't it? And this is dh dt. So nice. So I can just plug in 0.4 times 0.4 plus dV dh, h is a constant, so this is just going to be pi r squared over 3, and dh dt is 0.5, so we have it there. Okay, so I'm not going to get the actual answer, but let's just plug in everything we have. So we have 2 times pi. What was the radius at that given moment? Was 4 times 8 over 3 times we have 0.4, right? And the radius was 4, so we have pi 16 pi over 3 times 0.5, right? Okay. So, right. So you could do some cancellation, obviously. Let's see. We're going to have 8 pi over 3 from here. We're going to have 32, 64, 64 over times 2/5. Let's do this. 64, that's going to be 128 over 15, I believe, pi, plus we said 8 pi over 3. Okay, so excuse my algebra here. This is going to be 40, so this is going to be 168 pi over 15, I believe. Okay, if I didn't mess this up, right? It should be, oh, sorry. You didn't see any of that. Well, maybe there was some reason why you didn't see any of that. Okay. So that's the answer. That's the answer we get. Of course, if you're an engineer, you're going to plug in some approximation for the value of pi. If you're a mathematician, you're never going to touch it. You're just going to leave it as pi. I'm a mathematician. I'm not going to plug it in. That's what it be. Okay. And I think that's about it for the multivariable chain rule. I'll see you later in another section. Take care. Bye-bye.